Welcome to week 3 of our blockchain course. This week, we're focusing on cryptographic foundations that make blockchain systems secure, immutable, and trustless. Cryptography ensures the integrity, confidentiality, and authenticity of data in the blockchain. By the end of this lesson, you will understand cryptographic hashing and its role in blockchain, learn about public key cryptography and digital signatures, explore Merkle trees and how they enable efficient verification, and lastly, write a Python program to implement and validate cryptographic techniques. A cryptographic hash function is a mathematical algorithm that takes input data of any size and produces a fixed size output, a hash, is deterministic. The same input always produces the same output, is irreversible. It's practically impossible to reverse engineer the input from the hash, and collision resistant. Different inputs produce different hashes. The role of hashing in blockchain is two things. We have data integrity, where hashing ensures the integrity of blockchain data. Even if one bit of data changes, the hash changes entirely. And immutability. Each block's hash is linked to the previous block's hash, forming a chain of hashes. Altering any block invalidates the entire chain. Here's an example of SHA-256 hashing in Python. So first we would import the hashing library, hashlib. And as you can see in this code snippet, we have data equals blockchain security is awesome. And that's just a string that the input that we want to hash. And again, it's just representing the data. The next line is actually hashing the data, where we apply the SHA-256 hash function to encode that data. And as you can see, the hex digest right here, this just means that it's going to convert the hash object into a hexadecimal string. And then lastly, we're printing the result in a SHA-256 hash along with a hash label. And once you run this code here, you'll get something as such in the output. As you can see, we have SHA-256 hash in the actual hexadecimal hash. Public key cryptography, or asymmetric cryptography, involves two things. A public key, which is shared openly and used for encryption or verifying digital signatures, and a private key, which is kept secret and used for decryption or creating digital signatures. Where we apply public key cryptography in blockchain would be in digital signatures, where a private key signs a transaction providing ownership, and the public key verifies the signature's authenticity. And also wallet addresses, where wallets generate public-private key pairs. The public key is hashed to create the wallet address. Let's talk about a digital signature workflow. Now, one, a user hashes the transaction data. Two, the hash is encrypted using the sender's private key to create a signature. 3, the signature is sent with the transaction. 4, the network uses the sender's public key to verify the signature. Let's take a look at this example of signing and verifying data in Python. Let's go over this code. So we have import RSA. Now, we're going to import the RSA library, and these are tools for public key cryptography using the RSA algorithm. We're going to generate keys, and this code right here just generates a pair of keys, a public key and a private key, which creates a 512-bit RSA key pair. And this is a small size. We're just using it for demonstration purposes. The private key is used to sign a message, and the public key is used to verify the signatures, and it's shared with others. Next line, we have to create a message. This converts the string into bytes using the dot encode parentheses. because cryptographic functions work on byte data, not the plain string. So it has to convert it. Sign the message is the next line of code where it's going to use the private key to create a digital signature for the message. The hash of the message is calculated using the SHA-256 algorithm. The hash is then encrypted using the private key to create the signature. Next code is verifying the signature. Now, this takes the message, the signature, and the public key, recomputes it, and then decrypts it. And if it matches the signature, it's valid. Again, this is just verifying that the message was not tampered. And as you can see here, it will print the result with print signature is invalid or print signature is valid. When we talk about RSA, it's just an asymmetric encryption algorithm. It uses that public key for encryption or verification, and it uses the private key for decryption or signing. It's a widely used cryptography algorithm for secure communication and digital signatures. Now, you may ask, why sign a message? Well, signing ensures integrity, the message has not been altered with, and authenticity. The sender owns the private keys and is who they claim to be. When we talk about why verify a signature, verifying proves the message is authentic and untampered, and the sender is legitimate. Just remember that RSA works in three main steps: key generation, encryption, and decryption. Now, let's just go back over Merkle trees. Now, we know a Merkle tree is a hierarchical data structure used to organize transaction hashes efficiently, summarize all transactions in a block with a single hash, which is called the Merkle root, and enable quick verification of transactions without processing the entire block. How it works is each transaction is hashed. Hashes are paired and combined to create a new hash at the next level. And then the process continues until a single hash, the Merkle root, is created. Now, we use Merkle trees to verify, to have efficient verification. So instead of downloading the entire blockchain, a node can verify a specific transaction by checking the path of the Merkle. And even if a single transaction changes, the Merkle root changes. So it'll definitely detect any type of tampers. Here's an example code of building a simple Merkle tree. As you can see here, we have our importing of the hash library. We're defining a function to the hash data where it converts the string to bytes and returns the hash as a hexadecimal string. As you can see here, we already went through that. The next line of code is just defining transactions where these transactions will be hashed and included in the Merkle tree. We're also calculating leaf hashes, which is going to compute the hash of each transaction string, which is the leaf nodes of the Merkle tree. And each hash represents a unique fingerprint of the transaction. Then we're calculating intermediate hashes. This combines the hashes of adjacent transactions. As you can see, hash 1 and hash 2. You can see hash 3 and hash 4. Now, the next line of code is calculating the Merkle root. This combines the intermediate hashes, hash 1, 2, and hash 3, 4, and hashes them to form the Merkle root. The Merkle root is the topmost hash of the tree and represents all transactions below it. Next line of code is just printing the Merkle root. The output is the final Merkle root, and you're going to see it in your terminal or console. Here's an example of what the output may look like if we run this code. We see Merkle root and the hash. The key concepts here is a Merkle tree is a binary tree where each leaf node is the hash of a transaction. Each parent node is the hash of the child nodes. And the root node, the Merkle root, is the final hash representing the entire tree. Remember that the Merkle root is important to blockchain because of efficiency and integrity. The Merkle rule allows verification of individual transactions without downloading that entire blockchain. And if any transaction changes, the Merkle root will no longer match, which will reveal a tamper. Some real-world example would be in Bitcoin. The Merkle root is stored in the block header and represents all transactions in that block. Here's an illustration of the Merkle tree. I know we went over a lot, but just a summary to make sure you understand this illustration. Each transaction is hashed to create a leaf node. Adjacent hashes are combined and hashed to form parent nodes. This process continues until a single Merkle root is obtained. The Merkle root provides a compact and secure representation of all transactions. Let's do a quick activity with some practical exercise on implementing blockchain security. So in step 1, we would create a transaction class with digital signatures. And as you can see, our class is our blueprint for creating our object. So we have class, transaction, and we're calculating hash, we're signing transactions, and we're definitely checking the digital signatures if valid. In step 2, we're just going to validate the signed transactions where we have to create and sign a transaction, as you can see, the public key and the private key, and then verify the transaction, and it's going to print transaction is valid, transaction is invalid. All right. Now, I do have the full code for you to copy and paste in the resource folder, but I want you to download the file, review it in your IDE, save it, and run it. And in your terminal, you should receive something as such. And as you can see, it shows the begin of the public key, the end of the public key. So that's the full public key that is shared. And then it shows the transaction is valid. Just run this. All you have to do is download it from the resource section, save it, and run it so you can see the output. But also pay attention to the code, because what I'm showing here is just part of the code. And there are some other things that may be interesting for you to learn. Here's a tip. You may have to install the cryptography module with Python. So you can go ahead, pause this video and run the code, and then we'll on to our homework assignment. So for our coding assignment, we're going to extend the transaction class to include a method for generating a Merkle tree from multiple transactions. This will be the transaction class from the code that we just saw, we just went over. You can also write a function to validate a specific transaction against the Merkle root. Remember, I do have this code in the resource section so you can see what the outcome will look like. And just in case you have any issues, you have something to guide you. Another thing is your reflection task. Write a 300-word essay explaining the importance of cryptographic hashing in ensuring blockchain immutability, and how public key cryptography secures transactions and prevents fraud. Next week, we'll explore how peer-to-peer networks power blockchain systems. We'll implement a simple distributed network of blockchain nodes and simulate block propagation and consensus in Python. Let me know if you need any help with this week's exercises or concepts.